According to the American Heart Association, there are about 3 million people worldwide with pacemakers, and 600,000 pacemakers being implanted each year. Like several biomedical implants, the pacemaker requires a battery in order to perform. Today, batteries and pacemakers will last 5 to 10 years, after which the patient must undergo surgery for battery replacement. As longevity of the population continues to grow, the number of battery replacement surgeries performed will increase, leaving cardiac patients with more bills to pay and higher health risks due to chance of infection. Scientists and engineers today are attempting to address this issue either by improving the current batteries or by harvesting ambient body energy. These new sources of energy must display biocompatibility, long-term stability, and the ability to be integrated into biomedical devices, as well as be able to consistently provide sufficient power. Current research has focused on harvesting body energy primarily through enzymes or microbes. The principle behind enzymatic fuel cells is that enzymes, in place of metals, can oxidize fuel. A glucose biofuel cell based on enzymatic principles has so far been successfully implanted into rats. These fuel cells run almost solely on sugar and oxygen found throughout the body. Enzymatic fuel cells were first promising due to being very inexpensive. However, due to difficulty stabilizing enzymes, these fuel cells have short lifetimes and poor power density. On the other hand, microbial fuel cells in large scales are already in use. These fuel cells are based off of chemical to electrical energy produced by microorganisms during the degeneration of matter. Like most fuel cells, the process requires an anode, cathode, and ion-specific membrane. Research has shown that these fuel cells, implanted into the large intestine, could provide a source of power for biomedical devices. Issues in this area, however, include both the bulk of the fuel cell itself and the specificity of where it can be placed. For example, a pacemaker, usually placed just below the clavicle, would have to be connected to a battery in the large intestine. In the next 2 years, these two types of fuel cells will hopefully become smaller, more efficient, and longer lasting. Research is currently looking for ways to stabilize enzymes which would thus allow enzymatic fuel cells to become long-lasting and easily implanted. By providing patients with lifelong energy to their biomedical devices, scientists and engineers today will be reducing surgical costs and health treatment for a huge number of people around the world. With this new technology, there could be fewer patients in need of constant hospital support, and other areas of biomedical technology will be one step closer to efficient and effective internal health support systems. These battery alternatives are both healthy and clean while reducing current costs.